Welcome everyone. Welcome back. This should be Moonscapes number 44 if I think I got the number right. It's May 23rd, 2018, and we're dealing with a moon that's just past quarter phase. Right now we're sitting on the northern section of the moon. We got a beautiful view of that's Plato, well, right near the terminator, over near about 10 o'clock in the field. And if I bring this the right way, bring it down, right there, that crater, the Flatford crater over near 11 o'clock now, near the terminator, is Archimedes. Now when I refer to a clock face here, for those of you who aren't familiar, what I'm saying is 12 o'clock is right up in the middle at top. 6 o'clock is down at the bottom of the screen, right in the middle. 3 o'clock would be on the right-hand side of the screen in the middle, and 9 would be on the left-hand side of the screen in the middle. And then, of course, 1 and 2 would be in between 12 and 3 and such all the way around, just like the face of a clock. So when I refer to, like Archimedes now, it's approaching, it's drifting off to the about the probably 10 or 11, about 10:30 position on the clock. It's right near the screen's edge now and drifting to the edge, so to give you an idea. I'm trying to position this a little better, so let's see, that might be better right there. First off, let me apologize for my video just about 2 nights ago, my first one since I came back. I made a very big rookie mistake. All my years in astronomy couldn't cover this one up. I actually misidentified. I remember, those of you who saw that video or are going to take a look at it, you'll see where I was having trouble identifying 2 craters. Well, the problem was I said we were going to the south pole of the moon, and we were actually headed towards the north pole. The problem was that I have a map that let's zoom around while I do this a little bit, and then I'll come back and we'll talk some about things. I have a map underneath that I use. It's actually a computer map. There's the Apennine Mountains and the crater Eratosthenes right up near the end of the mountain chain. And what's nice about it is you can bring it up and match the screen on the computer to the image in your telescope. In other words, every number of reflections in your scope, it reverses the image back and forth and so forth. So you can bring this computer program up, and it throws the moon's image. It matches the time on the clock from the computer. It displays the moon just as it's going to be visible on this particular night, with north, south, east, and west. And you reverse it any way you want to match the view that you have on your computer screen. Well, I had forgotten I had to invert the screen, and I was actually trying to name the craters that were actually, they were wrong. We'll go down and take a look at those in a few minutes. But anyway, in my defense, I never did a lot with the moon when I was started astronomy years and years ago, 1956, and in my early years into my teens. I guess I was 12 years old in 56. And I did, at that point, I knew the moon much, much better than I do today, because it's the first thing you really look at astronomically. That is Clavius up on top, that beautiful, huge crater, right up near the top of the screen, drifting slowly towards the top. Let's pull it back a little bit. You can see the impact craters inside that. But anyway, I'll zoom in on that as we're going along here too. So, but you play with the moon a lot when you first start out. Then you get interested in the planets, you start doing the planets. And then with me, it was, I got into deep sky objects, nebula, and then eventually constellations, galaxies. And we're zooming in now on Clavius. That's a beautiful crater. So anyway, I got interested in research work, and my big research projects were dealing with variable stars, stars that change in brightness as the stars go through. And our sun does the same thing, but it's in a stable middle life now where it doesn't vary at all, or very, very little, so minutely that we don't notice it. And I began a study program on these, and I got involved heavily during the days of photography, and then with the CCD, where I did a lot of photometric work, and I worked with a couple of worldwide organizations, the American Association of Variable Star Observers, the Center for Backyard Astrophysics, Columbia University, I'm going to zoom in all the way. This is all the zoom I have, but look at that. That is amazing. Vanderbilt, the astronomy department at UCLA. So I got involved with some pretty heavy research work in variable stars. So at that point in my career as an astronomer, amateur astronomer, the moon was a nuisance to me. In other words, when the moon was in the sky, it's, as you know, it's bright, and at full moon you could actually walk around and see a shadow from the moon, and you don't see many stars because the moon is just, blocking them out. So that's my excuse. I've kind of forgotten about the moon until I've gotten here near the end of my career, and I'm back doing some lunar videos. But anyway, let me see. I want to make sure I do what I wanted to tonight. We talked a little while ago, not a little while ago, actually, my last video, and we talked about a few things, and we will tonight also. I want to talk about craters and how they're formed, impact craters and how they're formed. We'll discuss those in a minute, but let's zoom around and look at some of the detail we got tonight. I want to just, okay, give me 1 second. I'm going to pull my map back up, just so I can, let's see, what did I do with it? I buried it back underneath these. Give me a second to find it here. I'll be right back. I want to just check I want to check the orientation of one of the craters and make sure I'm right here before I corner myself again. No, I was correct. Okay, that's fine. Let's go back to the lunar image. And, okay, Clavius, as you see now, is drifting up near the top and going out of the field. And now, just touching the screen at about 10 o'clock, that is the crater Tycho. And that's got a beautiful central peak in it. And that's what we're going to talk about in a little bit. We're going to talk about how these craters formed and why we have central peaks in some of these craters. You get some wild theories in some of these sites lately about these central peaks. They just don't understand how they're formed and they're natural. But as we look around here, there's another large crater right below Clavius. See, Clavius is now being cut off at the top of the screen. Let's bring it down. Okay, that crater, that flat forward crater that is right near the top of the image now, almost touching the top. I'm going to bring it back down, but keep your eye on that. That is Magnus, the crater Magnus. Now, I have to go back to my map to get the diameter of that, but Clavius, I believe, is 137 miles across inside. Let me just check Magnus. That's a big crater, too. And let me, what do I do, flip my moon map? Let me see. What do I do here? No, okay. Let's see. The crater Magnus. Okay, I got it here. It's, no, okay, that's not what I want. There it is, okay. It is, yeah, it's 99 miles across that crater floor, Magnus, that flat-floored crater. And I just want to check the diameter again of Clavius. I think it's 137. Let me get it back here to Clavius. Why is this doing this to me? There we go. Okay, Clavius T. It's doing the same thing. Clavius D. Why is it? One thing about this map, those little craters inside, they all have their own designation. In other words, Clavius is the main crater, and then if you click on these little small ones, there we go. Now I got the main crater Clavius. The problem is some of those craters you click on it, and you pick the little crater, and it gives you the diameter, not the crater Clavius itself. Yeah, it was pretty darn close. Clavius is 136 miles in diameter. It's a huge crater. That's almost the size of the state I live in, the state of Connecticut. Probably is as big. And we'll zoom around a little bit more. Let me see. I want to make sure I don't lose you guys. Yeah, the moon's starting to drift now as I get back to my computer screen. And here we have that brightening problem again as we get to the edge and off the terminator over to the bright side. And let's see if we can adjust up for some of that and get rid of some. Whoa, a little too much there. Let's drop this down. That's too much. Not enough. Why is that not working? There we go. Okay, let's turn this up and back down. Pull it down slowly. And there we go. Now we got the detail on the edge of the moon. And as long as we're there, let's roll down this side, and we'll come to one of the very interesting parts of the moon right there. That is the Mare Crisium. It's actually a huge impact basin, but notice, this is one of the things we're going to deal with tonight, notice that crater that looks very white, and look at the circular pattern of Mare Crisium. And in Mare Crisium, use Mare Crisium as the face of a clock, and look at about the 10 or 11 o'clock position of Mare Crisium. You see that white blotched crater, and it's got that very wide open V white pattern in it. That is the crater Proculus. That is an impact site, and it had a very low angle impact, and the ejecta is those two white lines going out. And the ejecta pattern is very low, because you can tell just by the way that forward of that crater up towards the top of the screen, or to the upper left of that crater, you can see it V's out and there's no ejecta thrown out on the floor. That's because of the angle that the impactor came in. And so we'll come down here. We'll get over, if we move over here, I say I got to clean this eyepiece a little bit. I got a little bit of dirt on it. Wow, there is the nice divider between Mare Serenitatis and Mare Tranquility. And it's got that bluish look to it. And if we boost the color contrast, here we go. Let's boost it and see what happens here. We can start, the other night it was really bluish when we were out here. Let me see if I boost it up pretty good here now. There we go. Yeah, it's not quite as prominent as it was the other night, but there you can see that. Let me do something here. Let me see if this helps it. Oh, washed it out way too much. No, we don't want that. Let's turn this back down. Okay, exposure. We're having a little trouble. Maybe it's a contrast problem. Let's try and boost the contrast to here. Yeah, there we go. You can see the blue now. That's always fascinated me. But again, this is really, really enhanced color. That's not the true color of that Mare. Just take a little sip of my juice here. And again, you can see how tough it is to control the exposure. Those bright areas really, they really get bright when you get into this. Let me turn the, I'm sorry, I'm kind of thinking to myself as I'm doing this. And we have to really, there you really turn it down in there, and now you can see those white patches, those white little dots. For some reason, I got some people I see online, and they're on YouTube, and they're saying they're lights. Well, tell me, first of all, why would you have your lights on in the daylight? And if they were lights, let's go over and look on the dark part of the moon on the other side of the Terminator. Okay? Now look at those bright spots. See how they stand out? Now you can see all my dirt, my eyepiece when the moon's moving. Now look at here at the Terminator. Just to the left of that Terminator line, the sunrise-sunset line, what do you see? Nothing but blackness. If they were lights, don't you think they'd be on now? Okay, that's enough of an argument for me. But anyway, they are impact points on the moon. And the reason they're so bright and white is because when you have an impactor hit the moon, it raises very fresh material, which when it's hit by a sun angle, it makes it look very, very white. So that's the reason for that. Now, let's get over near the Terminator and start looking at some of these craters and get to what I wanted to talk a little bit about. Now, if you go up here and we look at, make sure I get all the way up there first. Get over here. Okay, Clavius is up near the top. Okay, let's zoom up a little bit so we can get a little better look at these craters. Clavius is on top, and it's going out of the screen as I zoom in. Look at that crater in the middle. That is Tycho again. And look at that beautiful central peak. Now, most of them you see are broad and flat-floored and don't have central peaks. But there's another one down near 530-ish, right into the edge. It has a faint little peak in it. If we go back down here, there's a couple more. There's one right there. I believe that is, let me see. I believe that's Theophilus. I could be wrong. But I don't. And then we come down here. That big broad crater, I believe, is Ptolemaeus, that big flat-floored crater, which is just coming up into the center now. And then as we get down in this area here, there's the Alpine Valley, the Alpine Mountains again. And over here, there's a nice, I believe, another one. That's Archimedes. No, I think we got to go a little lower. And I'll get you the name of that when we get there. Now I want to show you this other. That is Plato. Oh, by the way, those two craters right there, almost just off center of the screen, just to the right, those are the two craters I was trying to get the name of. Let's pull those up and see what they were. Those are the two I misidentified because I was on the wrong side of the moon. Sorry about that again. Those two craters are, and I'm looking at the atlas, I got to get back into that area. The top one is, let's see, my glasses, I can't read it, so I'm going to bring it. Eudoxus. The smaller one towards the top is Eudoxus, which is 41 miles in diameter. The one below it is, let me get the pointer on it, and I can bring. I can't read. I can see it now, but I can't read it. I got to get the pointer on it and get the enlarged writing. Yeah, it's Aristillus, and that crater is 53 miles in diameter. Those are the two that I totally screwed up the other night, and I'm sorry about that. But anyway, I just gave you the right name of those. But anyway, let's get back to our image and the central peaks. And we're losing the image. Got to bring it down. I wanted to show you there's another one real nice down here, crater with a central peak in it. Let me get over here. Let me get back over here. Yeah, there it is, right there. See, let's see. Okay, that's Archimedes, the flat-floored. Then there's a crater off of it, which is, I'm going to go back to my map. If they don't drift too much on me. Come on. Oh, I'm having trouble with my mouse. Here we go. I want to give you the names in diameter. Okay, we had Plato, or Archimedes, I'm sorry. In the smaller crater next to Archimedes is, oh, this one's a tough one. I'm terrible at these names. Cyclists or something like that. Anyway, and that's about 24 miles in diameter. And the crater below it that has that central peak in it is Aristillus, which is 33 miles in diameter. But notice that crater also has a nice central peak. Now, let's go to the argument that I'm hearing on some YouTube sites about those. Let's turn the color down. I don't like it that high when we're working here on different things. Color intensity, let's turn it back to normal. Let's see, okay, about there. And as we're in this area, let me go back to Proclus 1 second, and I want to show you how well that stands out. There, look at that. I want to zoom in on that. Okay, see that? Probably going to have to turn the brightness down a little bit and make that a little. There we go. Let's zoom in on that. Look at that V pattern. That's a spray pattern from an impact. Don't let anybody tell you that's constructed sites. That would have to, oh my gosh, that would have to be 100 miles on the side. I mean, it's just ridiculous. That is a huge injector pattern from an impact. The problem with, when I was growing up and getting into astronomy, back in the 1950s and into the 60s, early 60s, before we started the Apollo program to go to the moon, there was a huge battle going on as to how the craters on the moon were formed. And the two accepted theories at the time were volcanic and impact. And volcanic was actually winning out. But think about this for a minute. We're looking at craters here that, like Calavius is 136 miles across. Some of these others are 30 and 40 miles across. Where on earth do you find a volcano that big? And Earth is a lot bigger, has a lot more mass and gravitational pull, and it doesn't have anything near that size. So that started switching the thinking to, well, maybe they're meteoric. And, of course, once we got to the moon and really studied it, the earlier probes like the Ranger probes, the Surveyor landers, and orbiter probes, all the work from them showed that they were volcanic. And then, of course, when we landed, and they take materials and they put them under a microscope, the rocks that came back from the moon, and you can actually see in those little tiny micro pits where meteoritic dust falling on the moon because there's no atmosphere to stop it, and so it hits these samples at 20,000, 30 miles, whatever miles an hour they are, and it sandblasts them and leaves these pits in. Well, if you look at Earth material, Earth rocks, you don't have that, so that you can tell the difference in the two rocks that way. But anyway, once that was determined, the central peaks became an issue. And let's go back and get on that Tycho, the crater Tycho, and look at the peak while I'm talking about it. And how in the world, this is the argument, I just passed by something, I want to make sure it wasn't what I thought it was. No, okay, I'm all right. I was thinking of the straight wall. No, that's just a ridge in there, a little mountain range. I thought it was a straight wall, but that won't be out, I think, until tomorrow night. There it is. Let's bring it down a little bit more and take it over here. And let's look where the brightness is best. If I go this way, let's go. Oh, that's not what I want. I want this one. Come on. Oh, that's not what I want. Oh, I'm looking at the wrong bar here. Oh boy, come on, guy, wake up, will you? All right, that's what we want. Okay, that's a little too much. Let's bring it down here. There we go. Now, again, I did a lousy job on the alignment of my mount tonight. It's drifting on me like crazy. I got to keep recentering it. It's kind of a pain. Okay, but look now. Again, look at that peak in the center. Now, we've got these sites out there. Oh, that's alien construction. It's this, it's that. It's not natural. Yes, it is. It's natural. It's a process of some of the impacts. Their argument is, well, you have a meteorite or asteroid smacking into the moon, making these huge craters. How can you get something like that in the middle of it if you gouged out the hole with an impactor? Well, and this is the example I use. It was given to me a long time ago by somebody very knowledgeable in this field, and it's a perfect example. You can see it for yourself. You can see the process for yourself very simply. All you need to do is go take a walk if you have a nice still pond near you someplace. Find yourself a rock, good-sized rock, maybe the size of your fist, maybe even a little bigger, but as long as you can still heave it into the air pretty high. Get it high up in the air over the water, throw it up in the air, and then watch it carefully hit the water. When it hits the water, the first thing you see is a huge splash of water thrown out in all directions. That's your ejecta pattern that causes these white ray structures on the moon. And I got to be careful saying structures, because when I say structures, some people think of those as intelligent being structures, and no, that's not what I meant. That's not what I mean. Those are they are natural formations left by the impact. Now, after that rock hits the water and evacuates all that water, well, gravity doesn't like that. It wants to fill that hole back in, so it pulls the water around it back in. And watch carefully as that happens. Now, this happens very quickly, so you got to watch closely. When the rock hits, you get the large splash, the water rushes back in, and when it meets at the center, there is a rebound splash, and you'll see a stream of water shoot straight up in the air, right out of that hole where the rock went in. That shooting stream of water straight up quickly falls back in, because we're dealing with water here and the gravity of the Earth. But on the moon, when an impactor hits, it turns the lunar material into like a lava, sticky, or lava flowing like material. So when it lands and falls back into the center of the crater, it piles up. It leaves this pile in the middle, and hence it cools, and there's your central peak. Well, a very good question is, well, how comes all the craters don't have them? And it's a good question. If you look carefully at a lot of these craters, especially some of those more small ones, a lot of them do, but a lot of them don't. And that's simply a matter of the what's the word I'm looking for? The physics of the impact. It depends a lot on the mass of the impactor, the speed, what the speed is when it hits the moon, and its angle of attack when it hits the moon. Now, you notice that was another argument a lot of people make. Well, if these are impacts, how comes they're all round? If you have an impact that hits at a sharp angle, How comes we don't see elongated craters? Well, you do. You can look hard, you can find them, but they have to be very shallow. If you get an impactor hitting at about 45 degrees, it still makes a round crater. It may throw a little more material off to one side, but the crater left over is still round. And I want to show you something tonight if it shows up well. Let me get over to this side, and I got to find the right mar first. And there's a crater that shows us very well if I can get it to show up tonight. Let's see. I got to get down here. And yeah, there it is. I see it. Going to get it right in the center first. Whoops, wrong way. You're doing really good, Jim. I'm going to leave it there because it's going to drift towards the center. Let's zoom in a little bit. And then I'll have to enhance this image. Okay, now it's going off to me on that side. Let me bring it into the center. Let's play with some contrast. Yeah, there we go. A little more. And a little more. Okay. Now, see, I still got some zoom, so let me get it in the center again. See those two little dots right in the center of the screen? Let me zoom in on them. Okay, see the two dots? Now they're slightly off center of the screen. Notice the ray, the white ray pattern that shoots up to the left of it, going up to about 10 o'clock position. If you look carefully, and if I can get enough contrast in this image, it might be too much. Come on, it's drifting on me now. Come on, get back here. Let me see. If you look carefully at that, that ray pattern is actually divided. And there's a good reason for that. There should be a dark line in the middle of that word, and if I can get this contrast a little better or something to, let's see, maybe exposure. No, that blasted it right out. We don't want that. There, okay, you can see it a little bit there. It's, boy, this thing is drifting like crazy on me tonight. Wow. Look carefully at it now. You can see that there's like a darkness in the center of it. It's not, and if I could play around with some of this, boy, oh boy, I'm telling you, that drifting is just driving me nuts. That drive should be, unless my batteries are getting weak in the mount, that could be, they're pretty old. That might be a problem. There you can see it. There's a gap in that ray, see it? And what's happened is the crater to the left was formed first. The one to the right and a little bit below hit second, and it hit at an angle, and the spray pattern or the ejecta pattern was partially blocked by the crater in front of it. So the ray that shot out went around the crater, and the crater protected the center of that line, and you know, it left a darkness on it because the ejecta was stopped by the formation of the crater walls, and so it left that kind of a dark line in the middle of that. If we could, fortunately I went with a little lower power tonight. If we had gone with a higher power, we might have been able to show that better. Let me try to play with a few things to see if we can get that even better. I don't know. Let's see if I go way up with contrast. That's there, but it's not really great. What's about auto? Let's try auto. What's auto going to do? Yeah, auto is no good because I'm way too close to the edge, and I got contrast way too high. Let's turn this down. Down. Too much. It's very touchy. Very touchy. Huh. Hey, look at that. When I get it that black. Okay, let's look at it that way. I got it way blown out now, way too much. But maybe this will show more of what I'm trying to say. There's that line. Okay, you can see the line. There's the two craters. Yeah, and now you can see it better now that I completely blew out the contrast. You can see the split in it, especially up near the end of the trail. So anyway, let's kind of get back to a more natural image here. We'll go back to the Terminator. Well, how far am I in? Oh boy. I don't know what it is. I just use track at a time when I get in here. It's just crazy. Let's, yes. Nah, boy, I don't like that. Wow, I don't like auto. Let's Let's get the image back for you. There we go. Contrast is really up too much. Let's bring that down. That's close enough for now. And let's back out a little bit as I finish this off. Okay. I don't really like that, but let me try. I'm going to try something here. Boy, oh boy. And brightness. There we go. I'm working here on auto now, and I turn the contrast and brightness down to match, so we could work on it. We'd just leave it at auto and let it do its thing. There's a beautiful alpine, or I'm sorry, the Alps. I keep saying alpine because there's a valley right off of this mountain chain, which will come into sunlight tomorrow, which is called the Alpine Valley. But anyway, that's the short story on craters and how they're formed. Their impacts. We've had a lot of volcanic activity on the moon. That's why you have all those flat mar areas. That's another contention with some people. Why do we have those? There was a heavy cratering period. We'll talk about that in another video. Very old area in our solar system where the moon got bombarded. So did the Earth, but the Earth has weather, and most of our craters have been weathered away. We still have a lot of them, like Barringer Crater in Arizona, and some bigger ones, Goss's Bluff, and I think it's Australia, and others. Here on Earth, but they get eroded away after thousands, tens of thousands, and millions of years. Where the moon is airless, it's a vacuum, and when they make the impact, the crater stays. And I gave you the story on the central peaks. They're natural, and I gave you the physics experiment that you can do on your own at a still pond where you have a still water, and you can see it for yourself. You can see that process in action yourself. So with that, guys, I'm going to sign off tonight. Again, trying to get back in the scheme of things here. There's that beautiful end of the mountain range, the Apennines, and that's the crater Eratosthenes. And look at that, and yeah, that's the one that's got the other nice. Let's close off, and I'll just enlarge this a little bit, not enlarge it, but zoom, and you can see that one has a nice crater pit. It gets a little washed out when I go up too far, but you can see Eratosthenes also has a very nice central peak. So that's it for tonight, guys. Thanks for joining me, and hopefully we'll have a weather might be coming in here. I don't know when. I'd like to do one closer to full moon when the crater of Aristarchus is out, and we can study those lunar ray patterns, especially from the crater Copernicus. Tycho's ray pattern is actually beautiful. You can't see it tonight. It's too close to a quarter phase. It'll come out closer to full moon. So hopefully we can do something with that a little later in the month. But anyway, guys, until then, good health to you all, and clear skies, and we'll talk to you real soon. Take care, guys.